Good morning, students. Welcome to the lecture of Real Analysis 1. We will have a look to the concepts we have studied in the last lecture. In the last lecture, we have studied two important theorems. The first one we have studied regarding the integrability over an interval and integrability over the two different intervals where the intervals are made by taking one point C in between the closed interval AB. The theorem says that if the bounded function is integrable on closed interval AB, then it is integrable on AC and CB, where C is the point in the closed interval. Also, we have proved that if f is a bounded and integrable on AC and CB, then it is equally integrable on closed interval A to B. And in both the cases, it is true that integration A to B f dx is equal to integration A to C f dx plus integration integration C to B f dx. We have seen the proof in detail. Okay. Also, we have seen one important lemma regarding the proof of showing integrability of product, quotient, and modulus of integrable functions. The lemma we have proved is oscillations of a bounded function of an on an interval closed interval AB is the supremum of the set. The set is mod of fx1 minus fx2. Whatever is the suprema of the set will be the oscillations. Right? Oscillations is the suprema of this set we have proved. Okay. In order to prove this result, first we have found the upper bound of this set m minus m, and in order to prove this to be suprema, that is least upper bound, we have shown that if we subtract a small positive number epsilon from the upper bound m minus m, then it will not be a upper bound. Okay, it will not be a upper bound. It means that this is one of the least among all the upper bounds. Okay, therefore here this lemma we are going to use in order to prove the integrability of product of two functions, quotient of two functions, and modulus of a function. So, okay, let us understand the meaning of this statement. Okay, oscillations, that is m minus m, is the supremum of this set mod of fx1 minus fx2. Okay, let us go for first theorem of today's lecture, proving the integrability of product of two functions. Let me write the statement. The statement says that if f1 and f2 are two bounded and integrable functions, on closed interval AB, then prove that the product f1 dot f2 is also bounded and integrable. Therefore, how many steps we should prove in this theorem? 2 steps to prove. In the first step, we will prove that this product f1 dot f2 is bounded, and in the second step, we will prove that the product is integrable by using that lemma. What about the integrability? Can students guess? If the two functions are bounded, what about their product? Will it be bounded, and what will be the bound of the function? Can anyone answer? Hello? Students, is the voice clearly audible? Na?
Yes, ma'am.
Yes, ma'am.
Suppose K1 and K2 are the two bounds of the function f1 and f2. Okay, K1 and K2 are the bounds of the function f1 and f2. What do you think? What about the bound of f1, f2 on dot f2?
K square.
K square. K1, K2 I am saying. Na? If you assume K and K, then it is K square. Good.
K1 into K2.
And it is K1, K2. K1, K2. Okay. Or one can select maximum among K1, K2 as well. Okay. Therefore, here we will go for step number 1 to prove that f1 dot f2 is bounded on closed interval AB. Okay. Now here we will first mention the bounds of f1, f2. I will write since F1, F2 are bounded. Since F1, F2 are bounded, therefore there exists k greater than 0 such that for all x in closed interval AB, mod of f1 of x is less than or equals to k and mod of f2 of x is less than or equals to k. K is the common bound I have assumed. Okay. Then what about the function f1 dot f2? To prove it is bounded, I will put it in the modulus. Therefore, f1 dot f2 operated on x. Okay. How can I write this as? This is f1x dot f2x. Okay, where I can separate this modulus over the product. Therefore, this is mod of f1 of x dot mod of f2 of x, but each one is less than or equals to k. Therefore, this is k into k. Therefore, one can say the bound for the product of two functions is k square. Therefore, here we have proved mod of f1 dot f2 operated on x is less than or equals to k square for all x in the closed interval AB. Therefore, f1, f2 is bounded. Or one can write by taking two different bounds also. Or suppose I will take mod of f1 of x is less than or equals to k1, mod of f2 of x less than or equals to k2. Here we have to write there exists k1, k2 greater than 0 such that. Right now, these two must be the positive constant. Okay. Then there is one way with the similar to the previous step. Writing mod of f1 dot f2 is less than or equals to k1, k2. Or in other words, in other way, I can select the maximum among the two. I can select maximum k1, k2. Okay, if it is maximum, then surely k1 is less than or equals to k, k2 is less than or equals to k. Therefore, both bounds for both the functions are satisfied. Right now, therefore one can write mod of f1 of x less than or equals to k, mod of f2 of x less than or equals to k. And again with the previous steps, I can write mod of f1 f2 operated on x is less than or equals to k square. Therefore, whichever the way you can write, you will get the function f1 dot f2 is bounded. Is that fine? Or you can write k1 dot k2, no doubt. Thus, f1 dot f2 is bounded. Therefore, the first step we have completed, proving the function, product of function is bounded. Now we will move towards proving this to be integrable. Therefore, I will write now to prove that f1 dot f2 is integrable. Okay. While proving the previous theorem of proving addition is integrable, difference is integrable, easily we have obtained the relation between the corresponding bounds. But here, in order to obtain the relation between these bounds of f1, bounds of f2 and bounds of f1 dot f2, we have to use that lemma. Okay, therefore let me write. It is given that the functions are f1, f2 are integrable. Therefore, we will select the partition over which the function is integrable. It is given that f1 and f2 are integrable on closed interval AB. Let t equal to, and I am writing a partition, a equal to x0, x1 up to x1 equals to b, be any partition of closed interval AB. The partition of closed interval AB. Now we will write down the bounds of the function. What are the symbols we have used for the bounds of f1? Dash, no, capital Mi dash and small mi dash be the bounds. Bounds, that is suprema and infima of f1. Okay, single dashes are the bounds we are using for f1. For F2 we are using double dashes. Mi double dash be the bounds of F2 and capital EMI, small emi be the bounds of F1 dot F2 on ith subinterval. Correct na? Of ith subinterval. These are the notations we are using. Okay. Throughout all the theorems we have used the same notations. Single dashes with the bounds of F1, double dashes with the bounds of F2, and without dashes with the bounds of the corresponding function. Whatever it is, addition, subtraction, product, etc. etc. Okay. Now in order to establish the relation between the bounds, okay, we will start with considering the fluctuations or oscillations of this function f1 dot f2. Therefore, we will write we have for all x1, x2, for all x1, x2 in ith subinterval, that is xi minus 1 to xi, xi minus 1 to xi. What should I consider? F1, f2 operated on x2 minus f1, f2 operated on x1. This process we are doing because the lemma says that, what the lemma says, I will just recall the statement of the lemma. Lemma says that the oscillation, that is capital M minus N, is the supremum of this set. What we have taken in this set? Modulus of difference of functions for two different values of the corresponding interval. Here also I am considering modulus of, here to the next step we will consider modulus. Here I am considering the difference of two different values of the function for x2 and x1. According to the definition, here I can write this to be f1 x2 dot f2 x2 minus f1 x1 dot f2 x1. Now the job we want to do is we want to separate these functions f1 f2. Now in order to separate these functions f1 f2, we are making an adjustment of adding and subtracting some term. Okay, what is the term we are adding and subtracting in order to separate these values? We want to separate the functions f1 x1 and f2 x2. Now here we are adding and subtracting a term f1 x1 and f2 x2. Same term I have added. Now I am subtracting. Okay. By practice, you will get this idea that why we are doing this. No? Adding and subtracting. Adding and subtracting f1 x1 and f2 x2. Okay. Now what we will do? We will try to separate the functions f1 and f2. Now for this, what we will do? We will take the terms f2 x2 and f1 x1 common from the first and last. Right? From the first and last term, I will take f2 x2 common, and what will remain with us? This is f1 x2, and here it remains as f1 x1. See here in a bracket we have collected f1 separately. Now from the remaining middle two, we will take f1 x1 common. If I take f1 x1 common, I will write f2 x2 addition subtracted with f2 x2. Correct? Now here also you can observe in the bracket we have obtained f2 separate. Is it fine to everyone? Okay. Now in the next step we will take the modulus. Taking modulus, we get. What we get if I take the modulus on both the sides? This is mod of f1 dot f2 operated on x2 minus f1 dot f2 operated on x1. Okay. If I take the modulus on this right side, let me separate this over an addition. And whenever we are separating this modulus over an addition, the equality becomes inequality. We are using a triangular equality. Therefore, let me write this is less equal by. Let me separate over this addition and over the multiplication as well. Therefore, here we will get mod of f2 x2 into mod of f1 x2 minus f1 x1 added with mod of f1 x1 into mod of f2 x2 minus mod of let's see what I have missed out. Here it is f2
F1
x
X2.
what I have missed out. F2 x1 it should be na. Sorry, so writing mistake. This is f2 x1. Therefore here it is f2 x1. Now it is correct. Therefore here I have got f2 x1. Because if both the terms are same, this will be 0, na? This is a mistake. Okay. Now I have corrected it. Now, next step what we are going to do, as we know the functions f1 and f2 are bounded, therefore this term must be bounded and is bounded by k. This is also bounded and is bounded by k. Now what the term remains? Term remains to think out about this one and this one. Now we will make use of this lemma. According to the lemma, we have already proved that we for the functions or if we have the set of this type, then oscillations will be the supremum of the set. And if the oscillations are the supremum, what are the oscillations of the function f1 over ith subinterval? Over ith subinterval for the function f1, these are the two bounds. Therefore, what will be the oscillations? Capital M I dash minus small m I dash will be the oscillations, and according to the statement of the lemma, this term must be less equal by its oscillations. This term must be less equal by its oscillation. Here also for the function f2, this term is having the this kind of set is having the suprema as the oscillation. Now what are the oscillations of the function f2 over the ith subinterval? Capital M I dash minus small m I dash. Okay. And what for the left also? For here I will write by lemma. By lemma. What lemma says that capital M I dash minus small m I dash be the suprema of the set for the function f1. Correct? And x1, x2 belongs to xi minus 1 to xi. We are considering over ith subinterval. What about this second one? Small capital M I dash double dash minus small m I double dash will be the suprema of this set. Mod of f2 x2 minus f2 x1. Right? For the same value. Okay. And what for this left hand side? Capital EMI minus small mi will be the suprema. Sorry, not less equal, this is exactly equal. Will be the suprema of the set f1, f2 operated on x2 minus f1, f2 operated on x1 for the same values of x, right? This is what lemma says. Now, if this is the suprema, therefore what about an arbitrary value of this set must be less equal by its suprema. This is also less equal by its suprema, right? Now, therefore let us just think of what will be my right hand side. The right hand side will be mod of f1, f2 operated on x2 minus f1, f2 operated on x1. This is less equal. Okay. The first term is about the bound, and we know bound for the function f2 is k. Therefore, the first term is less equal by k. Second term, we are writing its suprema. Therefore, this term is less equal by mi dash minus mi dash. Capital mi dash minus small mi dash added with again what is the bound for this function f1 again it is k, and this term is less equal by mi double dash minus mi double dash. Therefore, this is what an inequality we have obtained. Correct now? Therefore, what we have obtained, this term, if I consider this set for different values of x1, x2, this set is bounded above by this term. Means this works as an upper bound. But what we have written for the same kind of set, f1, f2 operated on x2 minus f1, f2 operated on x1, this capital Mi minus small mi is the suprema. Suprema means this is my least upper bound. Okay. And this term works as an upper bound. Then what is the relation between this suprema and upper bound? Hmm?
Less than equal.
Good. Thus we get what we get? Capital EMI minus small EMI is less than or equals to this upper bound. K EMI dash minus EMI dash added with K capital EMI double dash minus small EMI double dash. Is that okay? And if suppose you are writing different bounds for the functions f1 and f2, suppose for f1 you are writing k1, for f2 you are writing k2, then what are the corresponding changes here? Here it will be k1, here it will be k2. Correct? If what we have obtained by this, we have obtained the relation between the bounds of f1 dot f2 of f1 and of f1 of f2. Now, once we obtain the relation between the bounds, we know the next process. Can anyone tell me what's the next process? In addition and in the subtraction, what we have done? Once we obtain the relation between the bounds, we have to convert those bounds to sums, upper sums and lower sum. For that, what should be a process? What should be a step should I follow?
Summation, taking summation.
First you multiply by delta xi and then
Delta
take
xi summation.
then take the summation, right? So shall I do this process? Hence, now multiplying I'll call this as statement number 1. Multiplying 1 by delta xi and before writing and this I is taking the value. Yes, I taking the value 1 to n. N subintervals we have, right? And adding all such inequalities. Adding all such inequalities we have for any partition or any partition P, right? Now what I am doing? I am multiplying by delta xi. For every I, we will get one inequality and finally we are adding all the inequalities. Okay, therefore let me do a shortcut. I will take summation. Shall I separate also simultaneously? I am just reducing my work of writing. Correct, na? I am multiplying by delta xi and we are taking the sum over I equals to 1 to n. Okay. This is less than or equals to. K is independent of I, therefore let me take it outside the sum. Okay. Let me put a bracket here. K equals to I equals to 1 to n. Now here we are multiplying by delta x and we are separating as well. Therefore let me write this is mi dash delta xi minus summation I equals to 1 to n small mi dash delta xi added with. Still this term is remaining. Therefore again this k I am taking out and we are multiplying by delta xi and taking a sum over this term which gives a summation mi double dash delta xi minus summation small mi double dash delta xi. No doubt sum is from I equal to 1 to n. Okay, this is what the process we have done. Now let me write down these values as the sums. What about this left hand side?
UPF.
Yes, this is UP. Actually, F is not symbol we have used. Therefore, shall I write
F1
F1, F2? Minus LP F1, F2 less than or equals to K into. What about this one? Bracket?
UPF1.
Good. UP F1 minus LP F1. Okay. What about the second bracket? This one?
UPF2.
Yes, this is UPF2 minus LPF2. Okay. Let me call this as statement number 2. But what is the fact known to us that F1, F2 are already integrable? If these two terms are already integrable, what about this value by integrability definition condition? UP
Less
upon
than
minus,
epsilon.
this is less than by epsilon. This is also less than by epsilon. But if I write by epsilon, this will be epsilon into k plus epsilon into k. Therefore, it will give
Epsilon
us
by K.
epsilon by k. If I write, then k will cancel. This will be epsilon. This will be epsilon. Means it is 2 epsilon again. What should
Epsilon
we
by
get?
2K.
Epsilon by 2k.
Good. This is epsilon by 2k. Okay. Now I will write since F1, F2 are integrable. This is purely an adjustment, right now? Since F1, F2 are integrable for epsilon greater than 0, there exists a partition P with norm P less than delta, and by first form of condition of integrability, first form of condition of integrability, what should I write? UP F1 minus LP F1 is strictly less by epsilon upon 2k, na? Is there any need to by heart this value that for product of integrability of two functions, the term should be taken as epsilon by 2k? Is it a need to by heart this step? पाठ करायची गरज आहे का?
No, ma'am.
No. Okay. Therefore, here just to in order to adjust epsilon, we are taking the values likewise. Okay. Now let me put the value of this 3 in 2. Putting 3 in 2. What is the left hand side? UP F1 F2 minus LP F1 F2. Correct, na? Left hand side is UP F1 F2 minus LP F1 F2, and now is less than or equals. Now it is strictly less than, na? K into epsilon upon 2k added with k into epsilon upon 2k. K into epsilon upon 2k added with k into epsilon upon 2k. Now this k will get cancelled. Epsilon by 2 will give us epsilon, right? Therefore, what we have obtained, UP F1 F2 minus LP F1 F2 is less than by epsilon. Hence, F1 dot F2 is integrable. Correct now? Any doubt up to this? For proving product of two integrable functions is integrable. Okay. Here at these first steps, you have to keep this point in mind. These steps we are doing just in order to separate functions F1 and F2. Okay. Once we separate, we can find out the relation between their bounds using this lemma. Okay. And once we obtain the relation between the bounds, we can convert it to sums. Once we convert it to sums, it will be easy for us to write the next part of the proof. Okay. Any doubt about this theorem? We have proved that product of two integrable functions is integrable. Good. Now we will go for next theorem, proving quotient of two integrable functions is integrable. Okay. Let me write the statement. If F1, F2 are two bounded and integrable functions on closed interval AB and there exist this added condition is required to us. We first write the condition. There exists a number lambda greater than 0 such that mod of f2 of x is greater equal by lambda for all x in the closed interval AB. Then prove that f1 by f2 is bounded and integrable. Now one may have a question now why this lambda condition is added. Let me explain. See, whenever we are defining the quotient of two functions, when we say that the quotient is going to exist,
when the denominator is not equal to 0.
good, when the denominator is not equal to 0. Therefore, here also in our case, in order to make sure that the denominator is not 0, f1 by f2, whenever I am defining, here we are saying lambda is a number greater than 0. If lambda is greater than 0, we have selected function f2 such that it is greater equal by lambda. Greater equal by lambda, lambda is greater than 0. Therefore, what does this mean? The function mod of f2 of x is greater than 0. It means the function may take a positive value, may take a negative value, but it will not take anyhow a 0 value. Okay? Therefore, this condition of existence of a number lambda greater than 0 and mod of f2 of x is greater equal by lambda just ensures that this denominator under the consideration is not taking a value 0 for any x in the closed interval AB. It is not taking a 0 value in the closed interval AB. Okay? Is this understood? Lambda greater than 0, mod f2x greater than equals to lambda ensures that denominator is not 0 in this quotient of f1 and f1 by f2. Okay, let us proceed. Again, the theorem should be proved in two steps. First step, proving the function f1 by f2 is bounded. Second step, proving f1 by f2 is integrable. Okay, let us go for step number 1 to prove that f1 by f2 is bounded. f1 by f2 is bounded. What is given to us? Both the functions f1 and f2 are bounded. Therefore, let me write since f1, f2 are bounded. Therefore, there exists a positive number k such that, what such that? Mod of f1 of x is less than or equals to k and mod of f2 of x is less than or equals to k. Okay, k is the common bound I have assumed. One more condition is given extra, that mod of f2 of x is greater equal by lambda. Therefore, here I will write this is greater equal by lambda, which is greater by 0. Okay, and this is for all x in the closed interval AB. Okay, now to prove the product, to prove the quotient is integrable, let me write f1 by f2 in a modulus node of modulus f1 by f2 operated on x is actually defined to be f1 of x divided by f2 of x, right? Now I can separate the modulus over the division. Therefore, this is mod of f1 of x upon mod of f2 of x, right? Now, mod of f1 of x, this numerator is less than or equals to k. What about the denominator? Mod of f2 of x? This is less than or equals to k, but can I write it directly? I cannot write it directly, na, that it is less equal by k. Why? Because whenever we are taking the modulus, we know that the inequality gets reversed. Okay. But here, as mod of f2 of x is greater equal by lambda, here I will write the reason. mod of f2 of x greater or equal by lambda. If I take a reciprocal, what will happen? 1 upon mod of f2 of x.
Less than equal to 1 by lambda.
Good. This is less than or equals to 1 by lambda, right? For this numerator is less than or equals to k. This 1 upon f2 of x is less than or equals to 1 upon lambda. Therefore, combinedly, right? This is less than or equals to k by lambda. Fine?
Yes, ma'am.
What we have proved, f1 by f2 operated on x is less than or equals to k by lambda. Therefore, may I write f1 by f2 is bounded on closed interval AB. Now we will go for proving the integrability. Step 2, to prove that f1 by f2 is integrable. No doubt, again, for proving this integrability, we are going to make use of the lemma in order to obtain the relation between their bounds. Okay, therefore let me consider the partition. Let p equal to x naught comma x1 so on up to xn equal to b. We partition. Why we are writing a partition? Because we are interested in the ith subinterval. Rather, we are interested in bounds of the function in the ith subinterval. Right? So first, we are making clear what is the partition. Now let me write down the bounds. Let capital Mi dash, small mi dash be bounds of f1. Capital Mi double dash, small mi double dash be the bounds of f2 and capital Mi comma small mi be bounds of here I can write f equals to f1 by f2 on ith sub interval. Okay. Okay. Nowhere we are changing the notations for the bounds. Now, in order to obtain the relation between the bounds, we will go according to the lemma. Okay. What lemma? What should I consider for in order to use lemma? This is mod of f1 by f2 operated on x2 minus f1 by f2 operated on x1. How can I write this? This quotient is written as f1 operated on x2 divided by f2 operated on x2 minus f1 operated on x1 divided by f2 operated on x1. You have to take care that I should not write, there should not be a writing mistake by me. Okay. Okay. Now again, in order to separate f1 and f2, we are again making some adjustment. Okay, before making an adjustment, let me do a cross multiplication. What is a cross multiplication? f1 x2 minus f2 x1 subtracted with f1 x1 into f2 x2 divided by f2 x2 into f2 x1. Now in order to make the separation, I am adding and subtracting a term in the numerator f1 x1 and f2 x1. This is added. Now the same term I am going to subtract f1 x1 f2 x1. Let me complete. Okay. Is the point understood? In the last step, in the last theorem also, we have made a small adjustment in order to separate f1 f2. Here also we are making a small adjustment of adding and subtracting a term f1 x1 f2 x2. Let me write this, adding and subtracting. The term adding and subtracting the term f1 x1 into f2 x1. Okay. Now in the next step we will follow. We will just take some functions common. Now from the first and last. Why I am doing this? Because I want one positive, one negative. So this is a positive term, therefore I am taking a negative. If I take these two, there is nothing in common. Right? Therefore I am taking first and last. One positive, one negative term I want. Therefore, let us take common from first and last. What the term I can take common from the first and last term?
f2x1.
Good. F2 x1 I am taking common and the terms left are f1 x2 minus f1 x1. See, f1 is separated. Now from the middle two, which term I can take common? f1 x1 I can take common, right now. This is f1 x1. In the bracket we left with f2 x1 minus f2 x2. See, f2 is being separated, right? I will write the denominator. What is the denominator? f2 x2 minus f2 x1. Now we are in the modulus, therefore let us separate the modulus over this quotient and the addition. Therefore this equality becomes inequality, that is less equal. Now we will separate the modulus over every term. What is the modulus separation giving me? Mod of f2 x1 into mod of f1 x2 minus f1 x1. Correct? Added with mod of f1 x1 into mod of f2 x2 minus f2 x1. And the denominator also I am separating mod of x2 f2 x2 into mod of f2 x1. Okay. What about these function values? This is bounded by k, this is bounded by k, right now. And what about the reciprocal of f2? Bounded by 1 upon lambda. Already we have seen, na? Reciprocal of f2. Reciprocal of f2 is bounded by 1 upon lambda. Therefore, one can replace these values here. This is k, this is k, this is lambda into lambda, k upon lambda square. What about this one again? Now I am using a lemma. Lemma says that this term is less equal by its oscillations. Now what are the oscillations of function f1 on ith subinterval? Capital M I dash minus small m I dash. Right now, for here I will write by lemma. What lemma is? M I dash minus m I dash is the suprema of the set mod of f1 x2 minus f1 x1 x1 x2 in ith subinterval we have to correct. Right now this is by lemma. What for the second one? This is supremum of mod of f2 x2 minus f2 x1. Right now, and what for the left hand side? What for this left hand side? What is the least upper bound for this kind of set for different values of x1, x2? Mi minus mi.
Mi minus mi.
Mi minus mi is the supremum of f1 by f2 operated on x2 minus f1 by f2 operated on x1. This is what lemma we have written. Okay. Now let us make use of the lemma and the bounds of the function simultaneously. Therefore, above equation becomes. What is the above equation? Left hand side is f1 by f2 operated on x2 minus f1 by f2 operated on x1. Okay. Now we are writing. This is less equal already we have right now. This is k. This is also less than or equal to k. This term is less than or equal to 1 upon lambda, 1 upon lambda. Therefore, may I write k upon lambda square? Is that okay? This is k upon lambda square, and the suprema for this kind of set is capital M I dash minus small m I dash. If this term is less equal by capital M I dash minus small m. Right now, and what for the second one? This is also k upon lambda square, and this term is less equal by m I double dash minus m double dash. What we have obtained, this is k by lambda square capital M I double dash minus small m I double dash. This is what the relation between the bounds we have obtained. Okay. Therefore, if you look at this set, if I have different values of x1, x2, this kind of set is less equal by this term. Means this works as an upper bound. This works as an upper bound. But what is the least upper bound? This is the least upper bound. Same kind of set, na? So what is the relation between the upper bound and least upper bound?
Less equal.
Thus we get. Thus by lemma we get. What we get actually, least upper bound is less equal by upper bound. And what is the least upper bound? We know capital M I minus small m. And what is the upper bound? This side, right hand side. K upon lambda square dash minus small m dash plus k upon lambda square capital M I double dash minus small m double dash. Okay, here we have obtained the relation between the bounds of f, that is f1 by f2, f1 and f2. Can you tell me the next step?
Multiplying by delta xi
Good. I call
and
this as
converting
1.
it to upper sums.
Multiply by delta xi. I is taking the value 1 to n and adding all inequalities. See, the theme of all the proof is same, na? Once you remember the theme, there is no doubt to write the theorem, proof of the theorem, right? Now let me multiply by delta x and let me take a sum, and simultaneously I will separate the sum also. Therefore, this is summation I equals to 1 to n capital M I delta xi minus summation I equals to 1 to n small m I delta xi less equal by k upon lambda square is independent of I, therefore let me take it outside the sum. Summation k equals to 1 to n नंतर capital M I dash delta xi minus summation I equals to 1 to n small m I dash delta xi. Okay, one more term is remaining plus k upon lambda square summation I equals to 1 to n. Just wait for a few minutes. Sir, Hello. Sorry for the inconvenience. Let us complete the theorem. What the term here we will have? Capital Mi double dash delta xi minus summation I equals to 1 to n small mi double dash delta xi. Okay. Now what the sums will be? Corresponding sums will be? Please.
UPF1.
UPF. F I will call.
One.
F1 by F2 we have written F. Na?
Yes, ma'am.
Purposefully I have written F for this theorem. Okay. This is k upon lambda square. This is UP F1 minus LP F1. Right? Added with k upon lambda square UP F2 minus LP F2. But what the fact known to us, these two functions F1 F2 are integrable. Therefore, we can write the values in order to adjust this to be epsilon. Means F1 F2 are integrable for epsilon greater than 0. There exists a partition P with norm P less than delta we have. What we have? By first form of condition of integrability. What should be the adjustment one has to do? This right hand side we have to adjust anyhow to less than epsilon. Na? Therefore, what should be a term here? Is my voice clear?
Lambda square epsilon
Lambda
by
square.
2k.
Lambda square?
Epsilon upon 2k.
Epsilon upon 2k.
Good. Lambda square epsilon upon 2k. Similarly, for the second also, we have to write the same. Okay. Therefore, the above equation becomes. What this above equation becomes? UPF minus LPF is strictly less by k upon lambda square into what we have written epsilon square into epsilon upon 2. Sorry, lambda square into epsilon upon 2k added with k upon lambda square epsilon upon 2k. All the terms will get cancelled to one another and we remain with epsilon by 2 added with epsilon by 2, which give us epsilon finally. If what we have proved, the condition of integrability satisfied, that is UPF minus LPF is less than epsilon. Thus, F equal to F1 by F2 is integrable on closed interval AB. Okay, hence the proof of this theorem. Any doubt about the proof of both the theorems?
No, ma'am.
Once you understand the theme of writing the proof, all the proofs are going on the same line. Correct now? For addition also we have followed the same thing for addition, difference, quotient, and now product and quotient. Now we will move towards modulus in the next lecture. Okay, let me stop the lecture for today. Thank you for watching the lecture.